Mais alors là, le système, tu vois, là, l'épingle a cassé, je sais pas.
D'accord.
Si tu peux te le mettre à cette hauteur à peu près.
Ok.
Voilà.
J'essaie de pincer.
Voilà.
Nicola, la segretaria mi dice che devi pagare una sostituzione di parte. Saranno qui 1, 2, 3, 1, 2, 3, 123 quando vuoi, perché ti hanno dato dei buoni pasti nel tuo folder con cui puoi andare a mangiare, però costa 5 euro l'uno e a meno che tu non abbia detto non li voglio, questi buoni pasti sono già stati
Si, vas-y, j'écris le titre. J'écris le titre.
Rien à faire, c'est que les gens écrivent leur titre.
Voilà, exactement.
So now we are listening to Etienne. Mann is going to talk about quantum demodular. Or shall we have?
So thank you. So first I want to mention that this is common work with Thierry Mignon from Montpellier also. And I want to start with some introduction of what is quantum demodule. So last week there was some talk about with from YPLE about quantum demodule, also with Alessio Corti and Hiroshi Iritani. So I want just to make let's say to recall the basic fact for manifolds, and then we'll just go to a hypersurface. So let me start with some motivation. So the motivation is mirror symmetry. So if we start with what physicists call A side, so you take a projective smooth manifold. So in my mind I will take Pn, and then on the B side you have its mirror, which will be a Laurent polynomial. So in n variables, which is the following. So it's the sum of the coordinates plus q over, so it's dependent on the variable q, of the product of the coordinates. So the question is in which sense these two guys are mirror, and so there is many formulation of mirror symmetry, and the one I want to talk about is the quantum demodule framework. So here you know you can compute or define the quantum ring, and you have a Poincare duality also here. So this is Poincare duality, and out of this object you can construct a vector bundle. So let's call it donc construct a trivial vector bundle. So let me denote it F with a connection. So it was called the Dubrovin connection here. So I will define it again very precisely. What is it? What is the base, and so on. And also you can define some non-degenerating pairing S, which is related to this guy, to the Poincare duality. And then the question that you can ask is, can you cook also something like here? And you do. So you have also a vector bundle here. So here it's the Gauss-Mann system, the Brice lattice, sorry. So with the connection and also a pairing. And you can ask if they are isomorphic. So if you do that for Pn, they are. And there is many more examples where it's true. So namely from Hiroshi Iritani's paper, it is true for a weak toric orbifold, if I'm not wrong. So that's one object. And then you can enrich the picture and to add what it's called integral structure. So let it add Fz, so which is called integral structure. So Alessio Corti also used this last week. So it is a local system actually for this data. And on the other side, you can also have one. And in fact, more is true is that if you put the local system, then you have so here I put now my integral structure on both sides, and I have again an isomorphism. So this result is also due to Hiroshi Iritani, and the way he defined it. So actually, in his talk yesterday, he was talking about that. It was this gamma class, and one reason of defining it is because this corresponds to the natural one here. So that's the let's say the introduction. So why to put mirror symmetry in this framework? And there is one reason. It's a reason of reason. I mean, one paper of Kontsevich, Katsarkov, and Pantev, and maybe an earlier paper of Ertling or Ertling-Semenek, where people, so Ertling-Semenek, they consider only B-side, and they call this object, they call it terp structure. And so there is many variants of these kind of things. And actually, basically, the data are just a bundle with a non-degenerate pairing and an integral structure that should satisfy some condition. I will not explain the condition, but these are the initial data. And here is the same. And here, they call it variation of non-commutative Hodge structure. So there is, they have many reasons to call it like that I will not explain because I don't understand well all the motivation. But actually, that's what they believe, that there is many cases where you can construct this kind of thing, and especially that's why it's called non-commutative, because on non-commutative spaces you could do that. At least it's a conjecture that you can construct such data that are satisfying all the conditions. Okay. So let's now start my description on the. So I will just talk on the A side, and I will just define for toric. So the first part is to define this object for toric case. This is more or less. I mean, this is not more or less. It's exactly the work of Iritani. And then there is the second one where we just want to use a twisted Gromov-Witten invariance to do the hypersurface case, and you can also do some complete intersection. So let's do the first case is for a manifold, let's say. You can also do it for orbifold, but let's stick to manifold. So okay, so let me start again. So this x is a smooth projective variety, and you define the quantum. So let's put let TA a basis for the cohomology of X, and I denote also T sub TA like that, the dual basis. So now I will recall a bit what is quantum product. So just to put notation. So the small one actually, so it's dependent on the Q variables. So it's a sum over A, sum over D of QD, some Gromov-Witten invariance, G nu 0, and is this. So this is the quantum product. So I just want to introduce the Q. So there is many Q actually. So QD stands for this notation. QA, TA, where here you have R, and R is just the dimension of H2 of X. So I need this notation because this will be the base actually of my bundle. So let me just define now the bundle and the connection. So the bundle is very easy, it's a trivial. All the information are in the connection. So what you have is my bundle F is just, so the fiber is just the cohomology of X, and then I have a base space which is M cross C. So what is M is include C star R. So this is where the Q variable are. And here I have an extra variable, I call it Z. And so this M is actually where the quantum product is convergent. So if you like, For Fano, for example, you can take C star R. And now let's define the connection. So it's a trivial bundle, and the connection is defined as follows. So let me put two more notation. So I will denote delta QA, which is Q sub A d over d QA, and the same with del Z. So this is what people call the Dubrovin connection. So what is it? It's just you differentiate, and then you put plus 1 over Z, and then you quantum multiply by TA. Okay. So just recall that this guy, okay, because here, morally the base here, C star R, this actually you can see it like that. So morally the Q variables are in H2. So here these guys are just in H2. Okay. When you differentiate on the Q variables, you just quantum multiply by the H2 class. And then there is the, so this was yesterday in the Hiroshi's talk was when Z was 1, so there was this, exactly this formula. And then you can extend it on the Z variables. And you have the following formula. C1 of Tx, again, quantum multiplication. Then with some endomorphism mu. So mu is an endomorphism. And it's the following formula. It's the degree of TA over 2 minus dimension of x over 2 TA. Okay? So it's a diagonal endomorphism, actually. So it's very simple. And this, I mean, usually people call it Dubrovin connection or Giventhal connection. So this is part of my two data on the left here. Okay. So now let me state what is S. So S, if you take so for gamma 1 and gamma 2, two cohomology class, I will just define S of gamma 1, gamma 2 to be the Poincare duality. Okay, so let me use this. So this is defined on a constant section. And now the rules is that if you have a function you can put it on the left, on the first component with minus Z. So it's sesquilinear. So that's why it's not exactly the Poincare duality. There's a bit change. And on the right, it's like you can expect. So it's a sesquilinear form. Okay, so this is the definition of S. So S, what it does, if you look at on the fiber, it pairs a point in the fiber Q minus Z, so here. So this guy is in the fiber Q minus Z with a point in the fiber QZ. Okay. So of course then you do that globally and you define this S. So this thing is, because it's Poincare duality on constant, this is non-degenerated. Okay. So this is what people call so I don't know if you should call quantum D module D3 or then you should put this more, but sometimes people call that 3 guys quantum D module. Okay. So let me state some property about this object. So I learned them from Iritani, but maybe we can also put Giventhal. So the first thing is the connection nabla is flat. Okay. So just recall that something is a bit, in mirror symmetry in Gromov-Witten invariance, you want to package the Gromov-Witten axiom in some way. So if you do the product, you package some of the axioms, namely WDVV axiom. But so if you just keep the first line, so this is just exactly the same property of the quantum product, the mini WDVV. But with the other one, this extension somehow on the z coordinates, the fact that this is flat is using something more. So this uses WDVV. So somehow it packages the same information here, and plus topological recursion relation, okay, and divisor axiom. So what I point out is this extension here on the z coordinates just encodes something more, which is actually TR. So this is the first thing. The second one. So now I should do some diagram. And you want to find a solution. So Alessio Corti was talking about that last week, about how to find a fundamental solution of nabla. So let me just put that on a big diagram that helped me actually a lot to understand what happened. So when you have a flat connection, you want to find a map, a gauge transform that just change the connection. So here you have your connection, and you want to trivialize it. So of course, usually you need something. So you have a base here. You should do some universal cover, or let me put everything as I do a universal cover. So this is maybe a multiple value function, but let's do these things. So actually, what happened here is we have a middle guy. And the middle guy is just when you flat the q coordinate. Okay? So this one is the following. So it's d plus mu times c1 of tx over z, dz over z. So now when I have done that, I have done a flat change with a function that I will denote L. So I just flat the q variables. And then I want to flat also the z, and this is very easy. This is the map is just z minus mu z c1 of tx. Okay? So now if you compose these two arrows, you trivialize your connection. Okay. So the one nice fact is that you can have an explicit formula for L. So I will just give you the formula so that you will see that it's completely explicit. And that, as Waipili explained, just contains some one descendant Gromov-Witten invariance. So if gamma is a cohomology class, the formula goes as follows. So it's q minus t over z. So I will not explain all the notation, but just what happened a bit. So here appear a psi class here on this formula. So this guy make very, I mean, this is really the important part of this connection to flat it. Okay, this is L. You have a formula like that. Okay, so here you have one point descendant Gromov-Witten invariance. And then the third property is that this function is an isometry for S. So this is a very nice property because it helps you to compute the inverse. So this, if you look at it, what you find is that this implies that L inverse is the dual, the adjoint, okay? Because it's non-degenerated, you can do that. And now let me put the function that people were talking about, the J function in this picture. So the first thing you should understand in this diagram, so that the bundle is always the same, it's just the connection that's changing. So if you take, for example, whatever class, a cohomology class, it's a section here, it's also a section here, it's always a section here. So the J function, where it lives, it's the following. So here you take very important section, which is 1, okay? So if you remember Hiroshi's talk on the mirror symmetry, the 1 corresponds to the other side to the volume form. So this is very important section, and you consider it on the right, so here. And then when you put it back here, so you get what people call J. So the definition of J is just L minus 1 of 1, okay? So this is the definition of the J function. And then you may wonder, how can I invert that? And then the answer is here. You just compute the adjoint, okay? So then you have also a very explicit formula for the J function. Yeah, okay, so should, yeah, that should give him that, okay. So, okay. Yes. Okay. So, let me, okay. So now let's start with maybe a proposition, a theorem that comes from your paper. So it's the presentation when X is toric. What can you say? So. So, I don't know if this one is your theorem, so I will again say Iritani. So now let X be toric. And then you wonder, can you see this vector bundle? So a vector bundle with a connection is the first example of what people call a D-module. So you can ask yourself, can I present it in a nice way? And the answer is yes. So you do the following here. So it's not completely right. I should restrict to some open, but let's think it is. So here you take this this presentation. Here I have an ideal. I call it GKZ. Okay. Let's put it square D for D in H2 of X. And then I need another operator, which is this one. So the hat means the following. So here this is our operator, okay? Differential operator. So this means the following. So you have a class, so let's do it for Tx. You can just expand it with coefficient like that, okay, in the base. So this is the base. And then the hat means just you replace the base by some differential operator. So it's Z delta Q, okay? So this is the hat, sorry. So this is there is one operator here, and here a family. And let me also put a formula for this family. So this one is the product of row. So you have it's a toric, so you have some rays. So this is rays of the fan. So let me call that d rho positive, and this is just the intersection with the toric divisor of the following operator. So again, d rho, you can you transform it as an operator. And you have this formula. So here d rho is negative, so I should put a minus sign. Okay. So here, so this is the statement. So again, if you never saw this kind of operator, you feel like and so what? So this is a very special operator. It's called a GKZ operator. And this is a very classical differential system that people study a lot. I've studied a lot. So we have this presentation. Yes.
Do you need some kind of boundary condition? I mean, otherwise you would need like generalized mirror transform.
Yes.
I mean, toric. So I mean, toric.
Yes, you're right. You're right. You're right. Or Wifano.
That theorem is based on.
On given tal. Yes, yes. It's right. It's written in your paper, but okay. Let's write again given tal. I don't know when you should just drop given tal at some point, but I don't know. So let's just give you a feeling of what is this map, because this map is very natural. So this map is, you have an operator here, P. So this operator just depends on delta Q and delta Z. And you map to what? So QZ. And you just put QZ, and then you apply the connection instead of the operator, and you apply this to the section 1. Okay? So the favorite section that we have on the right. Okay? So this is this one. And how to prove that? So here there is some given tal mirror theorem hidden here, because when you compute this thing, so let me try to do a bit more here. Actually, this is L of QZ, and when you change with the L variables, so you trivialize the connection, and then the trivialized connection is exactly this one. So then it's exactly the same formula. So this is just tautology about L. And what happened here, so maybe in blue you don't see so much, but what happened on the right is you recover L minus 1 of 1, and this was just J function. Okay? So the first thing is, when you have this map, you can always define this map, and you can ask, does it killed by this operator? And the answer is yes, because this one is, let's say, the I function. So it's not exactly equal. You should have some mirror transformation to do that. But you have this I function. So for people who just wonder what is the I function, the definition actually is, you can find it in a classical paper about GKZ system. People just study this GKZ system, these kind of things, and they produce a solution. And this produced solution is completely explicit, and you have this statement. And so this result is due to given tal, this one. So it's given tal kind theorem of mirror symmetry. So you're always saying that J function is equal to I function. So this is kind of up to mirror transform, and this is kind of so this is the what you use in the proof to just say that the map is defined, and then you know the rank here. The rank here also is known by some other works, and then you can find that this is an isomorphism. Okay. What's B? P? What do you, P? It's an operator here. Okay, take an operator, I just map it. Okay. So now let's go to some twisted some twisted case. Okay. So this means for hypersurface. So mainly this part is something about, is also due to Giventhal, most of it. And there is some paper of Panaripande where is a Bourbaki seminar where he's explaining in this kind of setting the work of Giventhal. And that's what we use. So twisted Gromov-Witten invariants are used by many people. There is, for example, the thesis of Tseng that is using also twisted Gromov-Witten invariants. So there is many people that are using that. So let me state the hypothesis. So let X be smooth again, projective variety. And let letter L be an ample line bundle. Here you can also put some generalized E that split, but let's stick to this case, such that minus kx minus L is nef. And then you take the hypersurface, an hypersurface defined by a generic section. Of L, and let's call it I, the embedding in X. So now, if you look classical Lefschetz theorem, what you have is that the cohomology of Z just split in the image of I star, some direct sum kernel of the push forward, and this, and moreover, and that the kernel of I star is included in the middle degree. No, the of X. So we have that. So let me write the diagram that I will use actually to define several kind of objects with the twisted Gromov invariants. So what you have here, you can do the cup multiplication by C1 of L, and this is, of course, the composition of the pullback. So this is Z, the pullback and the push forward. And so here you have a kernel here, and I will define the H bar. Let me put here. Is just the cohomology defined by the kernel of this map here. Let's call it MC. So the multiplication by the cap multiplication by C1 of L. So C1 of L. And then what you have is that, so yes, so you have that map. And here you can restrict, so I will just restrict to what is called the ambient part of Z, which is by definition just the image of this map. So this map then is surjective. And this becomes an isomorphism. So F, if you put everything together, F is doing the following. You have a class gamma bar in this guy, and you just do the pullback of gamma. Okay, and this is an isomorphism by Lefschetz theorem. And so let me just now define you some some vector bundle with connection that I will use to state some theorem, and then I will define them more precisely. So we'll define three quantum D module, let's say. So the first one is on the hypersurface Z, you can perform the thing that I just defined, and you get a vector bundle with a connection and a pairing. But then you just restrict to the, so the cohomology is the cohomology of Z, but you just restrict to the amb, so this one. So this is a small piece of the cohomology of Z. So I call it QDM Z, so this will be a triple F, I call it FZ, nabla Z, and SZ, so the pairing. And the rank of this bundle will be exactly the dimension of the ambient part of Z, and which is also because it's an isomorphism with the reduce, this one. Okay. Then you can define another one, which I will denote XL. So I will denote it F twist, because it's defined by twisted Gromov-Witten invariants that I will define in some minutes. And the rank of this guy is just the cohomology of X. Okay. And then you can perform a last one, which I call reduced, and which is F bar, nabla bar, S bar. And the rank now is just the dimension of H bar. So I will define these guys. So the first one is very natural. The second one is, let's say, it's natural, but it's not doing the job we want, because what happened here, what is very bad, so the bad thing here, this is degenerated, as you will see. And so you don't want that. And now, so because then it doesn't fit. So you reduce, and this one is degenerated. It's non-degenerated, sorry. So doing this quotient here by Kerr mu C, what happens is just you are just killing where it's degenerated. So then it becomes non-degenerated. And then this one looks like pretty much as a quantum D module, and actually it is isomorphous to this one. So let me state our theorem. So the theorem is the following. So the first thing is the quantum D module of Z is isomorphic to QDM bar of XL. And the second one, if X is toric, sorry, then what we want is a presentation as before. So now we have a presentation of these two quantum D module with some again some operator. So let me just denote by E twist GKZ the ideal here. And so we have an isomorphism here. So this proof is pretty much the one I just explained here. So it's almost the same. And again, it's using a result of given tal that the G twist is equal via mirror map to some I twist. So this is okay. And then the main statement is that what happened here, because the rank is changing here. So what happened is that here you should mod out by the quotient ideal by this the map. So here I don't know how to write that. So this ideal, so this the definition of this guy. So let me write it here. So maybe you know what is quotient ideal. Here it's a bit tricky because we are in non-commutative case. So this means this is left quotient ideal. So this guy is just the operator, the P such that when you multiply on the left to P, you just go down to Gkz. Okay. So you should take the ideal generated by that. Okay. Okay. So then you have a map like that with isomorphism here. So to prove the first line is almost the same that here. To prove the second line, it's a bit more difficult, and the reason is that you should find the rank. So again, the rank, we know it here, but the question is what is the rank of this guy? And this, we didn't find in the literature this rank, so we should just try to compute this one. And there is some, so the first thing you do to prove that is you can prove that this is a covariant D module. And so this proves that it is locally free. So you have a locally free bundle on the left. So this is very standard. And then the question is, what is the rank? And then you need, because you know it's locally free, you just need to compute at one point. So the point you take is you take z equals 0. And when you mod out z equals 0, it's turned out that to be not no more commutative, non-commutative, sorry. You go to some commutative algebra question, and then you can compute it and find that it is the correct rank. And then that's why you have this map here. Sorry? Yes, so there is an issue about what happened, because you should also look to the q equals 0. So there is an issue about the large radius limit here. We should do that. Yes, yes. Yes, we extend to normal crossing divisor. So you should put z equals 0 and q also go to 0. Okay. So let's finish with. So there is one more statement that maybe I didn't tell you. What we can also do here. Let me put in red. We can also define. So I didn't talk about because Hiroshi told us yesterday about it. So here you have an integral structure here. So this one is defined by this one, let's say Iritani and independently by Kontsevich, Karsakov, and Pantev for Pn. So they define this one, and to understand what happened is that mean in this picture the integral structure is something you have many of them, and the one that you define is the mirror. I mean, is compatible with the mirror. So what you can do also here is you can define some, let's say, integral structure here. And because you do the quotient, you have also another one here. And via this isomorphism, this is compatible again. So let's put it here. Fz it just correspond to the one you can define here. Okay. So it's and the formula. So here the formula for this one, he was using gamma class of Tx. So I will not put all the formula. Oh. Something like that. Yesterday it was like that. So with this is some class. And here the thing you are changing, here you should take gamma at of L minus 1, and then you have the same formula. So all the twisted theory, actually it's almost the same formula that before, but you should change at some point some Tx by Tx, and you should twist with L. And just take care of how to do that. Okay, so now let me just be more precise and define these two guys. Okay, a bit more precisely. So what you do is the following. So first, I will define the twisted Gromov-Witten invariance. So this is not something new. And I'm using a Panaripande notation. So I put a tilde here on this class. I will tell you what does it mean. So this is a 3-point invariance. So this means the following. So you have the model space of map to X, the evaluation map, and then you twist by this class, so which is C top of L0 3D, and that depend on a number. So the tilde here, so here you have a number which is 3, and which just refer to the tilde here. So now I should so you see this definition doesn't look nice, okay, because it's not symmetric. And actually it's not nice, but we don't care because we know that it was not nice because this one is degenerated, okay? So we are not, I mean, this one is not the good one to look at. It's just that it's performed the quotient to the one which is good, okay? So let me define this. So as we saw last week, you have the universal curve, and here you have the bundle L, pi, and you just do the higher push forward of F star of L, and this I denoted by L0 3D. So now because L, so this is a vector bundle of rank the C1 of L cup D plus 1, and this is because L is ample or convex. In literature it's called also convex. Actually you just need globally generated. To do that. And then you have an exact sequence, which is the following. So if you compute the virtual class, the degree of the virtual class, you find that this one is not the good one, the good rank. So you take just the evaluation to the third mark point, and you get a bundle here. Okay, so this is the definition. This is the kernel of this map, which is just the evaluation to the third mark point. So that's how you define this one. And now this product is also associative. So there is a bunch of twisted axioms, and you can also perform this connection and so on. So let me again state the proposition. So is nabla flat, nabla twist is flat, so let me define it maybe. So again, you have, okay. So it's just the same formula as before, but you use the twisted product. And there is some twist here. So sorry, here I should. So that this is one of the change. Should care of. So before it was C1 of Tx. Now it's this guy. So if you think about it by adjunction formula, this will be just Tz when you pull it back. And then you have this mu twist, which is a bit different. So now it's the degree of T8, so this is what as before. And now you have this this term that was not. So the changes are this guy and this guy. Okay. And the S, so this is for the connection. The S, what is it? Is defined as the same procedure, but on the cohomology class, here you have you should cup by C1 of L. So that's why it is degenerated. So this implies, as I told before, this is degenerated. Okay. So now you have the same proposition as before. You have a proposition. You have one. This is flat. The second thing is that you have L twist QZ. So the same diagram, the fundamental solution is C1 of Tx tensor L dual, fundamental solution. Sorry?
You always mean C1L in the pairing because you use ring sometimes.
Yes.
You always mean C1L.
Yes. So I mean.
Or L rank 1 or.
Yes. Sorry. So you need C top of L.
Up there you use rank L, which seems to say that L can be higher rank.
Yes, exactly. So okay. So you're right. So this is the. So if you put L is a vector bundle now. Okay, so then this is rank of E, and this is C top of L. Yes, to generalize. Yeah, yes, you're right. So this is C top of L. And okay, this is a fundamental solution. So as before. So I don't will write the formula here, but you can imagine. And now you have also this. So that's one reason to put the twist here. But you can say, but why you want something non-degenerated? So you can remove that. But what we need in the in the first part of the talk is that we need to compute L inverse to compute. And the trick is that L was an isometry for S. So here we need that L twist is an isometry for S. And this is also true. But it's true only if you put here C top of L. So this is why we need to add this C top of L here. So this is S twist of gamma 1, gamma 2. And so this, again, this leads to compute J twist, which will be L twist minus 1 of 1. And which is actually, again, because of this, so you will get this guy. Now you cannot use the same trick as before because you cannot take the adjoint because this one is degenerated. So there is no adjoint here. So you are blocked here somehow. But then what the trick is that when you go down to a S bar, then there will be the formula as before the adjoint for the reduced one. So let me So then we get, so let me rephrase. So this is all this triple. F nabla twist and S twist. Okay. So then you do the reduced QDM, the one I call with the bar. Okay. To define that, let me just sketch a bit the formula. So here it's twist. Sorry, put twist. So the formula is the following. So the reduced now quantum products, if you want. And this one exactly is the one correspond to Z. So this will be symmetric and so on. So you expect something better. So you do this computation. So now you insert here. So before for the twist it was like that, and now I add C1 of L. And the trick is that what shall I? No, sorry. Let's put that. Sorry. T1 bar. Okay. And the definition of this. So I should define this guy. So it's what I wrote upstairs. You twist with C1 of L, but because of the exact sequence, I mean, this is completely symmetric. You can move the C1 of L with the tilde where you want, actually. So this is symmetric. And this is, so now this is a small proposition, which is not too difficult. And this is exactly the Gromov-Witten invariance on Z now. So this is on Z. So you have this relation now. So you see this formula is completely symmetric, and so this one also. So this is the reduced product, and then you have some compatibility, and I will finish the compatibility. And so then all this proposition just go through to the reduced one, and you finish. And so you have a nice quantum G module. So the proposition is the following: is that if I take the twist and then I take the class of it, this is the same as taking the reduced product, like taking the class, and then the corollary of that is that you just pass everything to the quotient. Is flat, is as before, as expected. And S bar is non-degenerated. Okay. Okay, and then you find that. So I restate that. This is just, namely with this kind of proposition like that, you are able to prove that these two are isomorphism. Okay, so this is the end. Thank you.
Questa cosa qua cioè è una cosa che funziona solo per i twisted Gromov-Witten balance in cui hai il bundle